Viscosity is the internal friction of a fluid which makes it resist a tendency to flow. It's basically the stickiness of a fluid. It is caused by the friction of the molecules that move against each other within the fluid. And because different fluids have different particle and molecular arrangements, they have different viscosities. Pitch, for example, is one of the most viscous fluids we know. There was an experiment that started 1930, and until the 28th November 2000, that is 70 years, only 8 drops fell. On the other hand of this viscosity spectrum, we have substances like olive oil and water, which is 2.3 times 10 to the power of 11 less viscous than this pitch drop thing. Every fluid has a particle arrangement, so that should mean that every fluid has a viscosity. Or does it? If we cool down helium, which is this gas that fills up party balloons and gives you this really squeaky noise, if we cool it down, and I mean really down, 279.98 degrees, then some interesting stuff happens. This beaker, which was perfectly able to contain the normal fluid helium, has struggled to contain it. This new substance, which is now a superfluid, just drips through. Now if we get a container that is able to actually contain this superfluid, guess what happens? The superfluid climbs up the walls of the container and drops out. Now don't ask me why this is happening, because I don't know, and nobody really seems to know, because that's some crazy quantum stuff. Yeah, it's a shame, but I mean, we can still get stoked on Stokes' law, which is this crazy, which is actually surprisingly simple. I mean, it shrinks down to this equation, which is U plus F equals W. U is the upthrust of the fluid and F is the viscous force of the fluid. And if we add them together and it is the same as the weight of the ball or the object that is falling down the fluid, it has reached terminal velocity. There are no unbalanced forces. The ball is not accelerating or decelerating. It is just continuing at constant velocity down. If the weight is bigger than the upthrust plus the viscous force, guess what happens? It accelerates. And we only use this scary equation to find the coefficient of viscosity of the fluid that we are using. Now, you might ask, why, Fabio, why are we even bothering with this viscosity stuff? One reason why we care about this stuff is because the viscosity tells us a lot about the material, about the fluid. If you don't know the viscosity of this fluid, you can't calculate how much power the pump has to have in order to pump the fluid around your house. Another reason why we study viscosity is because it can be used in quality control. For example, you're working in Charlie's Chocolate Factory and you want to make these really nice chocolate cookies. Now you don't want a cookie that has like a little bit bumps of chocolate and everything. You want a smooth, even chocolate surface. For that, you need to know the viscosity of the fluid of the chocolate dripping down onto the cookie. The only problem with the chocolate is there's isotropy. I don't know how you pronounce this word, it's here. And in chocolate, the viscosity of the chocolate changes with the temperature. So yeah, that kind of brings up some problems. But hey, let's end the video with a summary and not with the bad notes. You have learned what the meaning or what viscosity is. You have learned the most viscous and the less viscous. You have learned that superfluids are, as the word says, super, like super cool. And that Stokes' law looks super complicated but is actually pretty simple. And yeah, I hope you enjoyed it.